Inductance analysis of electric machines by classical and numerical methods. This video, number 29, is in part a digest or summary of a paper recently published in the European Power Electronics Conference in Hanover, Germany. It deals with the very important topic of the inductance of electric machines, which is constantly in the mind of the machine designer and of the control engineers responsible for inverters and motion control. We might think that this is an old topic with little scope for new thoughts or aspects. Indeed, it is an old topic, but its significance has remained high, and we see continual development in methods of calculation and interpretation. In the last 2 or 3 videos, we've been looking at windings and winding factors and the effects of the numbers of slots and poles. And this slide shows the rather jumbled relationships between manufacturing and design factors on the left and electrical performance aspects on the right. The chart is jumbled because the relationships are many and complicated, and there is really no simple linear way to work through them all. But I would like to introduce this video with reference initially to the equivalent circuit, and this is a concept of the equivalent circuit of one phase of a synchronous machine such as the IPM. We see the generated EMF with its fundamental time harmonic component and its other harmonic components, which have orders which may be both higher and lower than that of the fundamental. And we also see the resistance and several components of the inductance, all of which may include self-inductance terms and mutual inductance terms between phases. And the key idea here is the partition of the equivalent circuit into separate components. A very important idea here is the recognition of 2 classes of inductance parameter, which we can see in slide 4, which is a kind of roadmap. At the top in green, we have the terminal inductances, so called because they can be measured at the terminals. They include the phase self-inductance, L phase and M phase, and in synchronous machines, the synchronous inductances LD and LQ shown here. In non-salient pole machines, LD and LQ are both nearly equal to L phase minus M phase, although these relationships are modified by saturation. In salient pole machines, such as the IPM, LD and LQ are still related to L phase and M phase, but in a more complex way that takes account of space harmonic variation of the phase inductances with rotor position. In both types of machine, it is possible to measure all 4 of these inductances at the terminals, and it is also possible to calculate them directly using the finite element method without considering the constituent parts or components such as the air gap inductance, the slot leakage inductance, or the end winding inductance. These components are identified in slide 4 as partitioned components, reflecting the division or breakdown of the terminal inductances into separate elements. We've mentioned the air gap component and the slot leakage component and the end winding component, but another important component is the differential leakage or harmonic leakage inductance, which represents the effect of space harmonics in the winding distribution. A synchronous machine such as the IPM normally produces torque as a result of the interaction between the fundamental space harmonic of the air gap flux distribution, and the fundamental space harmonic of the armature ampere conductor distribution. And the inductance associated with that fundamental space harmonic of the armature ampere conductors is the so-called magnetizing inductance, LMD. Other space harmonics of the armature ampere conductor distribution produce flux linkages at the fundamental time harmonic frequency, but contribute nothing to the mean torque. And in the Blue Book and in the paper we'll see that some of these components for the surface magnet motor in particular can be calculated by methods attributed to Bernard Haig. Historically, before the widespread use of powerful finite element software, the terminal inductances were computed from the partitioned components, which were calculated in turn by means of specialized formulas or algorithms that constitute a large part of the classical theory of electrical machine design. So the historical calculation process could be seen as an upward migration in this diagram, and once the terminal inductances were known, the performance of the machine could be determined and its inverter control could be designed. For the machine performance calculation and the design of the inverter, we actually do not need the partitioned inductance components. Who, in fact, needs them? Obviously, anyone following the classical methods will need them in order to assemble the terminal inductances, as we've just described. But if we can calculate the terminal inductances directly using the finite element method, why should we pay any attention at all to the partitioned component inductances? Indeed, it appears that there are quite strong arguments to avoid them. The modern finite element process computes and displays the magnetic field in the machine in far more detail than in the separate component calculations. These component calculations are all based on quite severe idealizing assumptions which barely satisfies the fundamental field equations and which approximate the geometric shapes and simplify the BH characteristic properties of the steel. The very basis of partition, in which the flux linkage is divided into separate components, is quite shaky. There is but one flux linkage at the terminals of any circuit, and the partition into components is always arbitrary to a greater or lesser degree. The reality of the magnetic field is that it is distributed throughout the machine, throughout the physical volume of the machine, and not separated into lumped components as is assumed in the classical theory of the partitioned components. The same is true of the losses. Not only the Joule losses, but also the core losses and the parasitic losses such as eddy current losses in magnets. All these are distributions, and when we contemplate this fact, we have to admit that any simplified lumped parameter model will have limited accuracy and flexibility to deal with different geometries and different operating conditions. This principle applies at least as much to heat transfer and fluid flow processes that are at least as important as the purely electromagnetic behavior. So, having made the case for this modernist approach to inductance, let us pause to consider whether there are any redeeming features of the classical partition component approach that might justify its retention. I'm going to make a list of 3 arguments in support of the classical approach. The first is the theory of windings, that is, the disposition of coils and interconnectors, the layout of the winding. This is inseparable from the calculation of the air gap components of inductance, including the fundamental space harmonic and all the higher order and sometimes lower order space harmonics. The same coefficients that arise in the inductance analysis, the harmonic distribution and pitch factors, and sometimes the skew factor, are the same factors that appear in the analysis of the EMF waveform, and they also have a bearing on the cogging torque. It's impossible to make a satisfactory winding design without a proper calculation of these winding factors. And this remains the case even today with very advanced winding manufacturing methods such as the hairpin winding, which must still satisfy the classical rules and is still characterized by the same winding factors. And much of this theory is couched in terms of integer arithmetic, and none of it can be found in finite element analysis software. The second argument in favor of the classical partitioned components is that they help in the design of specific features of the machine. For example, the slot leakage inductance, as we see here in slide 5. It's possible to set up a finite element calculation bounded for one slot, to study the magnetic field distribution in the slot, and thereby to help improve the disposition of conductors within the slot. While this can be used to get improved accuracy for the conventional slot leakage inductance, including the mutual inductances between phases, it's even more effective under AC conditions in analyzing the proximity effect and skin effect in the conductors. Again, in the very important field of hairpin windings used in automotive electric vehicle traction motors, this is one of the most important aspects of the design of the layout and distribution of the interconnectors, as well as the physical size of the conductors and the calculation of losses. What we're describing is not pure classical design theory based on simplified field models, nor is it the whole machine finite element calculation of the terminal inductances, but a kind of hybrid approach that uses classical theory with some focused, bounded numerical analysis. But we're doing this with a partition of the field and its associated inductance parameters, and not with the whole machine. The finite element flux plot in slide 6 is another example of this kind of partition, where the numerical analysis results are confined to one region of the machine, in this case the end windings. Once again we have a hybrid approach, but we have partitioned the field to focus on one particular design region. And this brings me to the third argument in favor of the classical partitioned approach. It may very well be too expensive to run whole machine finite element models in the process of evolving, improving, or optimizing a design. It is often the case that many components in the machine are already fixed, for example the design of the laminations, and changes are being made only in the winding or the stack length or the operating conditions. In such cases, one can argue that it is not efficient to run a massively complex and often slow numerical analysis hundreds or thousands of times, with the complete solution being worked out from scratch every time. With 2D finite element calculations, the number crunching overhead is much less, and the repetition of every case ab initio may be acceptable, but with full 3D it must surely be a concern. Of course, we will soon run into the question of accuracy, and so although it may not be economic to run every calculation, every design iteration with full 3D numerical analysis, it may equally be uneconomic to build prototypes and products based solely on the inevitably inapproximate analysis obtained with quicker classical methods. Finally, I would like to discuss another aspect of partition which is necessary in understanding the behavior of synchronous machines such as the IPM, which comes down from the terminal inductances without any a priori reference to the partitioned components in slide 4. What we have here are surfaces of flux linkage calculated by the finite element method in the D and Q axes of a surface magnet motor as a function of the currents in the two axes, ID and IQ. This calculation was prepared for the EPE paper by Dr. Johannes Hermitshuisen of Siemens in Nuremberg, Germany. The two cases at the top represent the actual machine, while those at the bottom represent an artificial situation where the magnets are practically demagnetized. If we divide by the respective currents, we get the respective inductances LD and LQ as functions of ID and IQ, including the effects of cross-saturation. In the D-axis, there is an element of the flux linkage that appears when the D-axis current is 0, and this is the flux linkage due to the magnet, that is the open circuit flux linkage. We can see from the surfaces that when the current is flowing, there is in fact no unique way to isolate the magnet flux linkage from the D-axis armature reaction, although there are several practical algorithms described in the literature, including one in the EPE paper. The point here is that we have an example of a purely numerical process giving digital data that is partitioned to provide variable values for the terminal inductances LD and LQ and the open circuit flux linkage or EMF, without any reference to the classical partitioned components discussed in slide 4. But consider how we would use this data to improve the design of, say, the windings or the disposition of conductors within the slots, or indeed any other detailed aspect of the machine design. Would we do it by countless repetition of the finite element calculation in a series of numerical experiments? And would we plot graphs of the things we're interested in as functions of the dimensions and other details that we're able to control? Or would we turn to the classical theory of the partitioned inductance components to find theory and formulas to guide us through what could become a very large amorphous mass of digital data? I'm sure there is no unique answer to this question, and every engineer listening to this video will have his or her own opinion. So in concluding, I would like to acknowledge again that slide 7 is borrowed from the EPE paper, and it was created by Dr. Johannes Hermitshuisen of Siemens in Nuremberg, Germany. Although it does not use JMAG, it is very similar to the data presented in video 18, and also in the Blue Book chapters 7, 8 and 9. All of which use JMAG in the same way. Thanks for listening.